Hi everyone, this is Mrs. J, and today we're going to start finding volumes of rotated solids, and today we're going to use specifically the disk method. Alright everyone, I have a quick warm-up for you guys, so please pause the video and give it a shot. Alright, go ahead and check your work here. So just be careful with your bounded area. It's actually this small little sliver right here. So there's two ways you can set this up. You can either do vertical slices, so like this. Now if you do that, you have to be careful because it's kind of split up over two different areas. Here it's the your quadratic minus the x-axis, and here it's your linear minus the x-axis. So you can set up two different integrals like this and evaluate them separately. Or if you do horizontal slices, your linear equation is always to the right of your quadratic. So if you rewrite them both as x equals, you can do right minus left, and then you only have a single integral to evaluate. So it's up to you, but this is the way I would recommend. All right, so today we're going to take a step away from just the area under the curve, and we're actually going to be working with the volume of a rotated solid. So a rotated solid is something that you can create by rotating a planar region about a given line, commonly the x or y axis or any other straight line. So imagine here we have this linear graph y equals 3x, and imagine you found this bounded region, which is a rectangle or a triangle, and then imagine that we rotate it around the x-axis. So you could see that creates a three-dimensional solid that is a cone. And then imagine here we have this quadratic equation, 4 minus x squared, and then imagine you find that bounded region, and then you rotate that around the y-axis. So here you have another three-dimensional solid. So to find the area of these rotated solids, there's different approaches, but today we're going to be working with what's called the disk method. So we use this when the cross-section of our solid creates a nice little disk. So the important thing here, I'm going to highlight this, it's also in bold. Imagine that we slice our solid perpendicular to the axis of rotation. So notice in this example here, it's sliced vertically, and it creates these vertical disks. So it's just really thin circles. And then for this one, our axis of rotation was vertical, so imagine we slice it horizontally. We get disks that look like this. So then essentially we're going to be finding the area of those disks, and then we can we can set up an integral with that area over our given boundary. So sometimes our boundary is going to be horizontal, so we're integrating with respect to x. Sometimes we're integrating with respect to y. So you have to really make sure you understand how your solid is sliced and how we are integrating. So we're going to be sketching still. We need to make sure we have a good visual representation of what's going on so we can also visualize the solid that's generated. And then really the trickiest part sometimes is just deciding what your representative radius is going to be. So notice here when you have that horizontal disk, our radius is going to be in terms of x because it's a horizontal radius. And when you have that vertical disk, our radius is going to be in terms of y. But then from there, once you know the radius, or a way to represent the radius, we know how to find the area of a circle, which is pi r squared, and then we're going to integrate over the given region. All right, let's try one together. So we're going to find the volume of the region bounded by y equals x squared, x equals 2, and y equals 0, and then rotated about the x-axis. So we're going to start with a sketch. So here is the right half of our parabola here, because I know it's also bounded with y equals 0 and x equals 2. So like this. So here's the region that we're working with, right in here. So now imagine that we take this and then we rotate it around our x-axis. Okay, so you're going to end up maybe with kind of a circle shape that looks something like this. And you could see that as you kind of progress down or from the right to the left, the size or the radius of your circle increases. So here, the next thing we're going to want to do is find a way to define what our radius is. So we know that the radius for this circle would be the distance from here to here. So we want to describe that in terms of our functions. So we can see that the height, this height will always be the height of that parabola. So whether it's here, 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 the radius of our circle is going to be x squared. So our radius is x squared. So that means that the area of each cross section is pi times our radius squared, which is pi x to the fourth. So that represents the area of each cross section. But again, that cross section is changing as we progress over our interval. So our interval of integration is going to be from 0 to 2. So we want the integral from 0 to 2 of this area of pi x to the fourth and then dx. So that will take into account every circle from here to here with the height changing depending on what the given x value is. So again, the tricky thing for a lot of these problems is just looking at your picture, trying to visualize and decide how can we represent the radius of each cross section. So once we have our integral set up, the rest is just kind of plugging through it. So I'm going to always pull out my constant like this, and we can find our antiderivative. So pi times 1/5 x to the fifth evaluated from 0 to 2. So here, pi times 32 fifths minus 0, so 32 pi over 5. And we will want to make sure to say units cubed or cubic units. So there you go. So this is a really basic example, but the idea for each problem is going to be the same. Sketch your graph, find the bounded area, and then try to visualize what would happen if you rotate that, that bounded area around the axis. And then you define your radius, and then it's always going to be the radius of the cross-sectional circle over your given interval. All right, let's try another one together. So here, let's start by finding our bounded region. So we have this linear function, so 2x minus 2, so something like this. And then we have y equals 0, y equals 2, and x equals 0. So we can see that our bounded region is right here. Now for this one, we're actually rotating it about the y-axis. So just to kind of help us visualize, you know, if we were starting to rotate it and we're exactly 180 degrees to the other side, it would kind of look something like this. So it would start to include this area here, and then it's kind of rotated around, so kind of three-dimensionally it looks something like this. So you could see that here our circles or our discs are horizontal because it's always going to be perpendicular to our axis of rotation. So now we need to find a way to describe what our radius is, what the radius of our cross section is at any given height. So you'll notice for this one, our radius is horizontal. So if I want to describe a horizontal distance, I need our equation to say x equals, right? When it says y equals, this is the height of our function at any given x value. We want the width of this at any given y value. So I'm going to rewrite this linear equation in terms of, I'm going to solve for x, so y plus 2 all over 2. because I can see that my radius is going to be the horizontal distance between my linear function and my y-axis. So for this, in this case, our radius is simply going to be y plus 2 all over 2, which again is that horizontal distance from our linear function to our y-axis at any given height. So this time it's in terms of y. So that means the area of any given cross-section can be represented by pi times our radius squared. So now that we have a way to represent that area, we're going to set up our integral. So this time, imagine, we're stacking up our discs. They're going to actually stack up vertically. So we're going to integrate vertically, which means with respect to y. So here, our lower boundary of integration is y equals 0, and it stops at y equals 2. So from 0 to 2 of pi times our radius squared, and then dy. So I will pull out my constant of pi over 4, and then I'm left with y plus 2 squared dy, and we know for a definite integral like this, it's much easier for us to actually expand out that binomial. So y squared plus 4y plus 4 dy, and now we're ready to evaluate. So pi over 4 times 1/3 y cubed plus 2y squared plus 4y evaluated from 0 to 2. So that will give us pi over 4 times, let's plug in 2 first. We have 8/3 plus 8 plus 8 minus 0. So it ends up being pi over 4 times 8/3 plus 48/3. So we have 56 pi over 12, which gives us 14 pi over 3 units cubed. And there you go. So again, everything from here on down is just what we learned last chapter, how to evaluate a definite integral. So the setup is definitely the tricky part for these. So getting an accurate graph, visualizing our solid, saying, okay, where's my cross section? What is it? Is it horizontal? Is it vertical? And then finding a way to describe the area of each cross section. So again, sometimes we're integrating with respect to y. Like in this example, sometimes we're integrating with respect to x if our circles are stacking up from side to side. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, so go ahead and check your work here. So here's kind of what that shape will look like. So it's the triangle when it's bounded, and then we rotate it about the x-axis. So here, when we find our r, we do need to make sure that r is positive. So it's really going to be 0 minus the height in terms of x. So it's 0 minus our linear function, which gives us 1/2 x minus 1. So you always are going to do high minus low, just like when you're finding that bounded region with your integral. So it's always high minus low, and that will give you an r value that is positive. So here's the area of each cross section. So we integrate over the interval 2 to 6. And this one, our discs are stacking up horizontally. So we are integrating horizontally, which is dx. All right, let's try another one together. So here we're finding the volume of the region bounded by first square root of x, and then x equals 0, x equals 2, and y equals 2. And here we're rotating it about the line y equals 2. So let's find what our solid looks like. So here's our square root function, and then we have between x equals 0, x equals 2, and y equals 2. So here's our planar region right here, and we're rotating it about the line y equals 2. So we're rotating it over this line. So it would end up looking kind of something like this. And then we have our vertical discs like this. So that's what our general rotated solid would look like. So now our job is to find a way to describe our radius. So you can see that our radius is this vertical height. So we want to know what this height is at any given x value. So here you can see that, again, our radius must be positive. So the distance, the positive distance from here to here should be this minus this, right? From any radius here to here, here to here, here to here, those are all our radii. It's going to be this line minus this height. So to find this radius and to make sure it's positive, it's actually going to be 2, because that's the upper line, that horizontal line right here, minus the radical function square root of x. So that's a way to make sure that our radius is positive. Again, it's always top minus bottom. So the area of each individual disk is going to be pi times this radius squared. And you can see that we're integrating from x equals 0 to x equals 2. So 0 to 2 of pi times 2 minus root x squared dx. So to evaluate this, I am going to pull out the pi, and I am actually going to expand this binomial, so it becomes 4 minus 4 root x, and then plus x dx, and then it's much easier to find those individual antiderivatives. So we have pi 4x minus, here we'll keep this constant. We know that our new exponent, since this is 1/2, will be 3/2, so we'll multiply by the reciprocal of that to clear it, and then plus 1/2 x squared, evaluated from 0 to 2. So that's pi 4x minus 8/3 x to the 3/2 plus 1/2 x squared, evaluated from 0 to 2. And from here, we're just plugging in our numbers. So that gives us 8 minus, so here we have 8/3. We plug in 2. 2 cubed is 8. The square root of 8 is 2 root 2. And then here we have plus 2. And then when we plug in 0, everything is 0, so it'd be minus 0. So we don't have to worry about that. So here we have pi times 10 minus 16 root 2, root 2 over 3. And then from here, there's not a whole lot we could do to simplify. We could combine this into a single fraction if we want. So pi times 30 minus 16 root 2 all over 3. So we could also do that. But again, it essentially means the same thing. And then it's going to be units cubed. So you definitely need to be careful when you're defining your R value. If it's going to be the distance between two different lines, always do the top line minus the bottom line. All right, let's try one more together. So first, let's sketch our bounded region. So it's between y equals x squared, y equals 0, and x equals 2. So here's y equals x squared. And then we have, I'm just going to leave out the left half because I see that it's bounded at y equals 0 and then x equals 2. So it's just going to be this region right here. And then this time it is rotated about the line y equals 2. So it's rotated over this line. So it'll look something kind of like this. And then you can see that we have a horizontal disk, and then they're going to be stacked vertically. So now we need to find a way to describe this R value. So you'll see that it's a horizontal distance, so we want to know what x is at any given height. So we want to know the x value in terms of y. So for this quadratic here, we're actually going to want to rewrite it as x equals the square root of y, and I'm just going to keep the positive square root because we're just working with the positive half of our graph, so we don't have to worry about the negative half. So again, this function is the square root of y. This is what x equals 2, so we're always going to do right minus left. For our radius here, again, we want to make sure it's positive. We're going to do right minus left. So in this case, our radius is 2 minus the square root of y, which again represents the width at any given height. So that's why we rewrote this as x equals square root of y. So now that we know how to describe our radius, we can set up our integral. So we can see, again, we're differentiating with respect to y because our disks are stacking up vertically. So we're going from 0 up to 4. So from 0 to 4, and I'm just going to pull my pi right out front because I know it's pi r squared. Here's my radius squared, again, with respect to y, so dy. So again, for this one, I am going to multiply out that binomial. And then I can integrate with respect to y. So 4y, and same scenario as last time, so minus 8/3 y to the 3/2 plus 1/2 y squared from 0 to 4. All right, here we have 16 minus 8/3 times k. The square root of 4 is 2. 2 cubed is 8, plus 8. So that gives us 24 minus 64 thirds times pi, which gives us 8 pi over 3, and then we have units cubed. All right, and there you have it. So again, just remember, when your disk is horizontal, we need a way to define this horizontal distance. So we need to know what x is equal to. So that's why we're solving for x. So if that confuses you, remember, I need to know a horizontal distance. I need to know x in terms of y. All right, here's one last example for you to try on your own. So go ahead and pause the video and give it a shot. All right, go ahead and check your work here. This one is definitely a little tricky. So here's our bounded region, and again, we're rotating it about the line x equals -4. So it ends up being this conical solid that looks like this. So first, to describe our radius, we need to know a width. So I need to know x in terms of y. So first you need to rewrite this equation as x equals 2y. And if I want this distance, it's going to be the right function minus the left function. So it's actually going to be 2y minus -4, which gives us 2y plus 4. So that's our radius. So you could say I have pi r squared, and then I'm integrating from -2 to 0. So remember, our disks are stacking on top of each other, so we're integrating vertically here. And then from here on out, it's just evaluating this definite integral. You should get 32 pi over 3 units cubed, but definitely a little bit of a trickier problem. All right, that is all for today's video. Thank you so much for watching.